We're now moving on to graphs of functions. In particular, we'll be graphing linear functions and quadratic functions this term. We'll graph them not only by hand, but using technology. We're going to start by a brief review of graphing by hand, and we're going to use lines to motivate most of that. And then we'll move on to quadratic functions and parabolas. But before we get going, let's review what it means to graph an equation. Now, when we graph an equation, we're actually graphing the solutions to that equation. So let's review what a solution is. Right here, we have a definition. A solution is a value for the variable that makes the equation true. So for instance, 5 is a solution to the equation 3x equals 15, because when you put 5 into the x, you'll get a true statement, 15 equals 15. Now, when you have an equation with two variables, then the equation is going to have to, or the solutions to the equation is going to be made up of two values, one for each of the variables. And functions are all like that. The functions that we've been working with this term have an input variable and then an output variable. Now, sometimes you don't see that output variable y. In this first equation up above, I've written the function so you see the output variable as well as the function notation. But the function notation, as long as you see it, is actually a representation that there is a second variable. There is an output variable. Now, it doesn't have to be y, but we're going to start with graphing on the xy plane, so it makes sense to think about these as y values. So g of x is just another way of saying y, h of x is another way of saying y, k of x is another way of saying y. So when you see a function, remember a function is representing a relationship between two quantities, an input and an output. So when we have that, the solutions are going to have to be made up of a value for each, an x-y pair, or variables that you're working with for that particular function. You're always going to list the input value first, and then the corresponding output value second. So x, y, with a comma in between them, and then parentheses around them when you show a solution to an equation that has two variables. Here's an example. The ordered pair 4, 5 is a solution to the equation y equals 2x minus 3. The reason that is that when you plug the 5 in for y and the 4 in for x, you will get a true statement. And let's just calculate to see that. Now we automatically have 5, no calculation necessary on the left. And on the right, we calculate 8 from the 2 times 4, and we subtract 3 from 8, we get 5 equals 5, which is a true statement. So this 4, 5 ordered pair is a solution to the equation y equals 2x minus 3. Keep in mind, the reason I knew 4 was the x value is because it came first. Remember, the input value or the x value comes before the output value when you write an ordered pair. Now, an equation with two variables or a function is going to have an infinite number of solutions generally. And when we have an infinite number of solutions, we can't write them all out. So that's why we draw a graph, because the graph is the pattern the solutions will make in the xy plane. So a graph of an equation or a function is a physical representation of the solutions, or a visual representation of the solutions. When graphing an equation or a function involving two variables, the old standby method is the point plotting method. You can use point plotting for any equation you come across. And the idea with point plotting is that you're going to create a series of points for the function or the equation based on finding solutions. And often we organize the way we do that in a table. So here I have the function f of x equals 2x minus 3. Remember, f of x is just another way of saying y. So what I can do is I can create some solutions to this equation by picking an x value. And a good x values to pick are ones that are easy for you to calculate with. So for instance, 0, 1, 2 is a good start. So if I pick an x value of 0, I can plug it into the equation and calculate y. So y equals 2x minus 3 in the equation. If I plug 0 in, I get 2 times 0 minus 3. And finishing the calculation, 0 minus 3 is negative 3. So I get a y value of negative 3. That means I have the solution of 0, negative 3, and I can then graph that. So there's a single point. Now let's do 4 solutions and graph them all. If I put a 1 in, y equals 2 times 1 minus 3. 2 minus 3 would be negative 1, so I have a solution at 1, negative 1. If I put a 2 in, y equals 2 times 2. minus 3. That would be 4 minus 3, which is 1. So I have the solution of 2, 1. And then the next one, I could keep going and plug a 3 in, but don't forget, you can also plug negative values in. So let's just plug a negative value, say negative 2 in, just to practice this. Negative 2 plugged in would give me y as 2 times negative 2 minus 3. That would be negative 4 minus 3, which is negative 7. So I'd have a value of 2, negative 7. So there are 4 solutions, and then those solutions are points that we can graph in the grid. So when I graph those points, and I have a grid set up already, we are going to graph 0, negative 3, 0 on the x, and then negative 3 down on the y-axis. Then we'd graph the point 1, negative 1 right here, and 2, 1 right here. And what you see just even from those first 3 points is that the graph seems to be lining up. If we graph negative 2, negative 7, it ends up a little bit off my grid, but I can probably approximate it right there. A good idea, if you have a big empty space on the grid right here, is maybe plug in another point. So I could plug in x equals, if I do another one, maybe x equals 4. If I plug x equals 4 in, I would have a y value of y equals 2 times 4 minus 3. That would be 8 minus 3, which is 5. So I'd have a point at 4, 5. And let's take a look at that, 4, 5. Do you see how every single point here lines up? So what we're seeing is the pattern that the solutions make. And once we recognize the pattern, we can connect the pattern with a curve, or in this case, a straight line. So we connect it, just like connecting the points. So this ends up giving us a straight line, because this is actually a linear equation. A little reminder, linear equations are going to be equations in which the variables are raised to the first power and no higher. Lines can be graphed with as few as 2 points. To actually graph this, I really just needed 2 of these. Any 2 points, for instance, this one and this one, would have defined the line all by itself. Or I could have used this one down here and this one at 2, 1. That would have defined the line itself. So technically, you just need 2 points. But it's always good to have a third or a fourth to make a better graph, because if you have a third or a fourth point, then they're further away on the grid. You're less likely to have wiggle in the graph or error just from the points kind of extending the line past where the points are. Here's another example. We have the function g of x equals negative 2/3 x minus 2. So let's go ahead and find some solutions to this equation and graph the function with them. Now, we can use any x values we want and take that and put it in for x and calculate our y. It's always good to use values that are going to make life easier for yourself if you're doing this by hand. 0 generally is an easy value to calculate with. Forgot I was in green here. So let's plug in 0. The nice thing about 0 is that you're going to have the first, any place where you have x, that term is going to multiply out to 0. So negative 2/3 times 0 would be 0, and then minus 2 would just give me negative 2. So I have a point at 0, negative 2, right there. Graph it at the same time. Now, when you're working with a fraction and you know x is going to multiply a fraction, because you can pick any value you want, pick a number that is going to make that fraction go away. For instance, if I pick a number for x that is a multiple of 3, then the first thing that will happen, for instance, if I pick 3 for x, is that when I multiply that whole number, 3 over 1, times this fraction, negative 2/3, my 3's cancel and the fraction is gone. So I get negative 2 minus 2, or negative 4. So 3, negative 4 is another solution, and it's on the grid, and these are whole number values, so much easier to graph on the grid. 3 and negative 4. So another multiple of 3 would be 6. So I could plug in 6, negative 2/3 times 6 minus 2. Remember that whole number 6 is over 1, so the 3 goes into itself once and into 6 twice. Because I picked a multiple of 3, the denominator cancels. I get -4 minus 2, or y equals -6. So I have a point or a solution at 6, -6. So if I continue there, here's 6, -6 graphed. Notice something. Those 3 points are lining up. Well, this equation was a linear function because the x was raised to the first power. So any other points I find should stay on that line. If they don't, I have a mistake somewhere. Now, if I kept going and maybe picked 9, I'd be off my grid. So let's go back the other direction and maybe try -3. So I have done some calculations here. Here's a little more room for me to do the next calculation. Y equals -2/3 times -3. Remember that whole number is over 1 because I'm going to multiply it by a fraction, minus 2. So here I cancel the 3's. Now the negative and the -2 are going to make a +2, and +2 minus 2 is 0. So I get 0 when I throw -3 into the function. So my last point here, -3, 0, is on the x-axis, and it is also along that same line of what we were graphing. So once we recognize the pattern, draw what we see in terms of the pattern. Easier on paper than on a computer, I'll tell you that. Notice it's also much easier to graph this kind of thing on a grid. So I do recommend if you're doing this by hand, use graph paper.